In this video, I'm going to go through the notes associated with functions, and we'll talk about them in a bit more detail. And specifically, we're going to talk about how we can define our own functions. All right, so functions are these smaller, simpler subcomponents of a program. We typically define them to represent a single task, where we can treat them as this black box, this thing that, we don't need to understand the intricacies of inside. We can just treat it as this thing that, has this agreed upon interface and performs this task that we tell it to. All right, and so it's oftentimes used to break up code into chunks and make it a little bit more readable. And so what is happening is when we call a function, right, when we call something like digital write or digital read, Arduino will see that function name, and then what happens is it jumps to the code that is defined inside of that function name and execute the code inside of there. And so that's an example of abstraction. Again, this is kind of that idea of a black box where we don't need to worry about the nitty-gritty details of what's going on inside of there. We just kind of know what it does. All right. And so functions can come in a variety of different formats. There's these built-in ones that are provided to us by Arduino, things like digital write, digital read, serial.print, like all of those different ones that we've talked about. There are some that are included, and these are functions that are defined inside of libraries. So we've been doing a lot of examples with the servo library, and that's something that we include at the very top of our program. And then we have access to all of those functions associated with servos. And now what we're going to talk about is how we can self-define our functions. These are functions that we are going to define. We're going to associate some lines of code with that function so that we can call our own function, and it will go to that definition that we wrote and do those different things. Okay, and so what we're going to do is we're going to first look at how we can identify them and then how we can write them. So this is these are the different parts of a function that we've kind of talked about before, but we're going to get more into the details here. Okay, so every function is going to have a name. This is a unique identifier, and it follows the same naming conventions as variables. And so it has to be unique. We can't reuse certain names because then it won't know what function we're referring to. So we have to create a unique name. And then we have this special term called arguments. And what those are the inputs that we provide to the function, right? So some functions require arguments and some don't. It can have, 0, 1, 2, or many different arguments. These are the various values that we are providing to a function in order for it to be able to do its job. So something like digital write, that requires two values. It requires the pin number that we want to control and the value that we want to write to that pin number, so whether it is high or low. And then some functions also have a return value. These are the outputs that we get back from a function after it's done its task. And so things like digital read or analog read, those return something back to us about the value that was read from that pin. And so every time I talk about a function that we're going to use, when I give you a new function or when we're defining our own function, we're going to need to recognize these four distinct parts of it. So what the name of it should be, a description of what it does so we understand, the task at hand that it is performing, how many arguments it has, what are the types of the arguments, and then whether or not it has some return value and the type of the return value. So we've looked at this again before too, but if we were looking here for function definitions, what I see are two definitions of functions. So we are defining the setup and we are defining the loop functions. And we can tell because there's the name of the function here, and then there are these curly braces, which is helping indicate what lines of code are a part of that function. So these lines of code in between the open and close are part of the setup, and these are part of the loop. And so these are functions that Arduino requires us to define because setup indicates what code should run right at the very beginning, and loop defines what code should run at the very end. We're going to talk about how we can write some of our own functions here that are not just the setup and loop. That'll be more helpful for performing specific tasks. And then we also have a lot of function calls in this example program. So a function call is an invocation of a function. Basically, we're using the function's name and calling it, telling the Arduino to go run the code that's defined inside of that function to perform that specific task. And so if we look through here, almost every single one of our lines of code, or actually all of them inside of setup and all of them inside of loop, are function calls. Because we have the name right here, serial.begin, and then we have some parentheses here. And then the value that's provided inside of the parentheses is the argument. That is the input being provided to this function, serial.begin, to do its job. Pin mode is another function that we are calling, and then digital write, serial.println, and delay are all other functions that we are calling. All right, so that was kind of examples of function calls with a couple of function definitions, but here's a function definition example. This is actually the Arduino code that is behind the scenes that implements the delay functionality. This is the definition for the delay function that we call a lot to make our Arduino kind of pause before continuing on with the rest of the program. And so what this tells me here is this is the name, this thing in yellow where it says delay. The thing immediately before it says void. And this indicates the return type of the function. It tells us, whether or not it returns something and what the type of the value is it returns. And so void indicates that it does not return a value. We put void if it doesn't return a value. If it did return a value, we would put some data type here like int or float to represent what the type of the value is that it returns. So this says void because it doesn't return anything. But here we see that we have an input argument. So the name of the input argument, or the variable representing the input argument, is ms for milliseconds. And then unsigned long, this is just a special type of integer value that can hold more information. It can hold a larger value than just an int. But that is kind of what is going on in this definition. And then we have all of the code defined inside of here. And so if we're not writing it, the most important part of a function definition is this first line here, which is sometimes referred to as the function header or the function signature. Because what it does is it tells us what we need to know about the function to call it. It tells us if it expects any arguments, what the types of the arguments are, how many arguments it expects, and it also tells us whether or not it gives us a return value and the type of the return value, in addition to telling us the name. So the function signature or the function header tells us everything that we need to know. So let's kind of break this down in these two different parts here. So this is a function definition, kind of similar to the one that we just looked at, right? We could define our own function to implement the mathematical function for a factorial. And so in order to compute a factorial, we would create a name for a function. So here I just put factorial. And then inside of the parentheses, we indicate whether or not there are arguments, how many arguments there are, and the types of the arguments. So here there's just a single argument. We're going to perform the factorial of this value that is input to us that is referred to as n, and the type of it is an integer value. And then in between the curly braces, we would write all of the code to implement the factorial functionality. And then at the very end, we need to return back information, right? We need to return the result of that n factorial. And so what we do is here we say the type of the return value in this definition. And so I would put an int here because we're going to compute some integer value that is n factorial and return that back. So once we've defined that, once we've written this method signature or method header and then defined all of the code inside of there, what we can do is we can then call that function from another place in our code. So a function call looks like this. We've been doing that before. We would just say the name of the function, and then we pass in some value here. So if I wanted to compute the factorial of 5, what I would do is say the name of the function factorial, and then put 5 here in the parentheses. And then it goes behind the scenes, goes to where we defined factorial, executes the code associated with it, and then returns back that value, returns back the result of 5 factorial, which is 120, and then it would store that into this variable a. So that's kind of our order of operations, is it would perform the computation associated with calling this function and then store that into the variable here. So here we have our definition of the factorial function. So what we do is we have that same agreed upon interface or method signature method header, right? Where we say, okay, it's going to return some integer value because we're computing some mathematical expression, right? But it also requires some input argument here, some integer value that's going to be passed in. So we're going to use this value n and compute n factorial and return that information back. So its return type is an integer, its name is factorial, and its argument is a single integer argument that's referred to as n. So over here, when I call factorial 5, what's going to happen is that value of 5 is going to be stored inside of n, and then I can refer to that value as n throughout the rest of the function definition inside of here. Okay, and so what we're going to do is we're going to declare some new integer variable called result, and that's going to store the value that we are going to return back. And so what we do is we set up some for loop here to start at I equals 1 and repeat until I is no longer less than or equal to n. That is the value that we are raising it to. And then we're taking result, which again starts at 1, and multiplying it times that value I. So the first time we would be saying 1 times 1, then I would become a value of 2. So then we would be saying, okay, well, result's currently equal to 1, so we would multiply 1 times 2, and then the value of result is 2, and then I becomes 3, and then we multiply result, which is 2 times 3, and that's 6, and then I would then become 4, and then we multiply result, which is 6 times 4, which is 24, and then result is 24, I becomes 5, and we would still always perform this condition check here. So I is still less than or equal to n because it's both 5 and 5. And then we do the final multiplication here, which would be 24 times 5, which gives us 120. Then we add 1 to I, so it would be 6. And then 6 is no longer less than or equal to n because n is 5. And so then we're done. So result would have a value of 120 in it, and our loop is done. And we go down here to the very last line of code. And that last line of code has this special keyword here called return. And what that does is it gives back control of the program to whatever called the factorial function. So you will always see this as kind of the last line in a lot of functions here to return control back to whatever called it. But what it also does is it returns that value. And so it's expecting some integer value returned that is the result of this mathematical expression, right? That is n factorial. And we just said we stored that value inside of the variable result. And so what we would do is say return result. And so back over on this side, when we say int a equals factorial 5, it computes that value, returns 120, and then 120 gets stored into this variable a. And so that's kind of the basics of a function definition. So we could look at another couple here. Like here is one for power that performs like an exponentiation, right? And so if we think about it, even without looking at the code yet, we would kind of expect it to take two input values, like the base and the exponent. So what we want to raise some base power to by that exponent, and then we would expect it to return back one integer value that is the result of that mathematical expression. So an example call to that would be power, and then we provide two values. So say we want to raise 2 to the power of 3, then what happens is it then computes that value, returns back that value, and then we could again store that into some variable or do something else with it. And so if we look over here, our first line of our function here is this signature or header, right, that shows the same interface, right, where there are two values here, int base and int exponent, that are our input arguments, and then it's returning back some integer value. And so when we pass in 2, 3, what happens is 2 is then stored in this variable base, and 3 is stored in this variable exponent. And so it's kind of similar a little bit to what we just did, but in this case what we're doing is we're still declaring some integer variable called result that is going to be the value that we return at the end. But what we need to do is repeatedly multiply result times the base until we run out of exponents. So what we did is we created a control variable called I, started at 0, and continue to execute this loop until I is no longer less than the exponent, basically making us multiply 2 by itself 3 different times. That's how that would work. And then that loop would be done, and at the very end we would return that result here and give that value back to whatever called us. So say somewhere inside of our other program, like inside of loop, we would have this line, and it would go in here, perform this operation, and return that information back, and then we store that into A. This last example here takes one single argument, some string value that we refer to as name, and it doesn't return back anything. That's why it has this void here, because what this does is it just greets the person by saying hello plus their name and prints that out on the serial port. So an example of how to call that would be greeting, and then inside of the parentheses there, I provide my single string argument inside of the double quotes, and then it would do that. So if we wanted to see how this worked, right, we could pull up our editor, and I know these are kind of contrived examples that don't really use too much of the Arduino functionality. Like, we're not controlling any pins or anything like that, but I think this is a worthwhile example to go through. So what I did is I kind of copied and pasted the factorial, power, and greeting functions here. And like I said, they need to be entirely outside of the definitions of the setup and the loop. Every function should be defined on its own. And oftentimes what I do is I kind of put it down here at the bottom, because once I've defined this functionality, I can just kind of leave it down there and forget about it and just call it whenever I need it. So just to try this out, what I'll do is I'll say serial.begin here, 9600, just so we can print out those values and make sure that it works the way that we would expect. And so then I could say, all right, well, let's create some integer variable a and set it equal to the factorial of 5 to make sure that that works the way that we expect. And then we could print out that value that is stored in the variable a by saying serial.println a. And let's just go through and try all of ours here. So I'm going to do kind of a similar thing for power. So I'll say int b equals power to raised to the third power. And then again, we'll print out that result by saying serial.println b. And then our greeting here is just, we call greeting, and then inside of here we pass a string. And you can see the Arduino has picked up on the fact that we've written this stuff in the way that that it expects, right? So it says, oh, greeting is something that takes a string argument. It refers to that argument as name, and then it returns back a void value, meaning that it doesn't return anything. So because we defined this stuff correctly, the editors start to pick up on that fact and will help us when we need to call the functions that we wrote. All right, so let's try to upload this to our Arduino, and then we'll see if it prints out these values. And I put all of this inside a setup so that it just runs once and it doesn't continue to print those values over and over and over again. But if we go here to the serial monitor, let me try and reset it again and see if that works. There it is. So it prints 120, which is 5 factorial. Then it prints 8, which is 2 raised to the third power. And then it prints hello, Michael. So it seems like our functions are working correctly, and that's how we would define a function. And then we could always just use this anytime we needed to compute a power or factorial or greet anyone. We could just call those however many times we wanted to up here, and it's that idea of abstraction. We created these black boxes that perform this specific task that we can now just trust to work the way that they want, as long as we call them or invoke them in this way where we're providing the values that it needs and then getting the values back out that we want.